Having looked at integrals now, in both application contexts and how to estimate them using left and right-hand sums, we finally arrive at the fundamental theorem of calculus, which will give us a system for evaluating integrals exactly. So if we want to do these area calculations and all the properties they could derive from that, in other words, evaluating some integral, it turns out it's just as easy as plugging a number, a and b, so the upper and lower limits of an integration, into a new function. And that new function is not some mystery one. It's related in a very particular way. If we differentiate this new function, f, we get the integrand. And if we go from what we have, little f of x, to what we want, which is some big capital F here in our symbols that we're using, what we're going to do is anti-differentiate. So, in other words, if we want to evaluate an integral, we can do so exactly if we can find a related function based on what we were given, the function in the integral, if we can find a function that, if we were to differentiate it, gave us our integrand, then all we'd have to do is plug b, the upper limit, and a, the lower limit, into that function, and out would pop our area, distance, or whatever property we're trying to evaluate with that integral. And so this is why it becomes the fundamental theorem of calculus, because it ties the relationship between derivatives, which we've seen, and integrals. So think of the two directions we've gone in. If we have a function given to us, we can find the slope in f prime. If we're also given the same function, but we're interested in a different question, what's the area underneath it, we can do that by finding a new function which is the antiderivative, or one which, when I differentiate it, becomes our little f. Now, that's going to be the hard part. So let's write this out in a bit more detail here. This is the fundamental theorem. Along the way, we're going to have to find f of x, find capital F of x here. And that can be easy, it can be hard, or it can actually literally be impossible, at least to get a closed form for it. And then we are going to plug in the b and the a here, and that is always easy. So the fundamental theorem of calculus lets us trade this conceptual problem with a calculational one. Find me a function which, when I differentiate it, gives me my integrand, and that could take a lot of searching, or it could be really easy, as we'll hopefully see in a couple of examples. But once we have that antiderivative, we can simply plug in the limits of integration b and a, and we have the value of the integral. This will make a lot more sense in context with some examples.